Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face trending list, published on October 14th, 2025, just yesterday. The big hook is a simple training trick called Spatial Forcing that gives robots strong 3D spatial awareness from plain images, hitting an average success rate of 98.5% on Libero, while speeding training by up to 3.8 times. The paper is titled Spatial Forcing, Implicit Spatial Representation Alignment for Vision Language Action Model, and the implications for model training are quite significant. In short, this paper aligns intermediate visual embeddings to geometry-rich signals from a pre-trained 3D model, needing no extra sensors and yielding better data efficiency and real robot performance. Also, the authors shared the official GitHub. You'll find the full spatial forcing code with open VLA and Pi 0 integrations, clear environment setup, Libero data preparation, training and evaluation scripts, pre-trained checkpoints, and example commands. There are fine-tuning utilities, LoRa merge tools, and configs in VLA scripts and experiments. RoboTwin deployment code is noted as coming. You'll find 3 spatial forcing checkpoints for Libero spatial object and goal, each around 8 billion parameters, safe tensors BF16, plus simple code to load and run inference. Alright, Figure 1 shows how spatial forcing teaches a vision language action model to internalize 3D spatial structure without extra sensors. In panel A, the method aligns intermediate visual tokens to geometry-rich features from a frozen 3D foundation model, which injects depth-aware cues into the model's layers. Panel B reports faster training because the added alignment guides learning more directly, and it also lifts test accuracy over strong baselines. Panel C uses depth probing, a diagnostic that maps hidden features to depth values, showing crisper shapes when the alignment is applied. So, Figure 2 contrasts how robots acquire spatial understanding. The left panel feeds explicit 3D inputs like depth or point clouds, which require extra sensors. The middle panel estimates 3D with explicit assistance from a separate expert, so errors in that expert can leak through. The right panel uses spatial forcing, which implicitly aligns internal visual features to a 3D foundation model, giving spatial features without extra sensors at inference. So Table 1 compares methods on the Libero benchmark and shows spatial forcing leading across suites. The approach achieves about 99% spatial success, which essentially matches or exceeds explicit 3D systems while avoiding extra sensors. The gains cover object, goal, and long horizon tasks, so reliability extends beyond simple cases. This table supports the claim that implicit alignment boosts both accuracy and practicality. Well, Figure 5 shows that alignment makes training and data use much more efficient. The left graph plots success against iterations and reaches a target in about 3.8 times fewer steps. The middle graph plots success versus dataset size and achieves the same accuracy with about 5.9 times less data. The right TSNE plot, a two-dimensional map of feature similarity, shows matched cluster shapes, so the model gains spatial structure while keeping its own identity. Alright, 2 takeaways stand out. Aligning intermediate visual features to a pre-trained 3D representation yields strong spatial understanding without extra sensors, and it delivers practical wins with about 98% success on Libero and up to 3.8 times faster training. The broader implication is a scalable recipe for geometry-aware robots. That is it for the AI Research Roundup. I am Alex. Thanks for listening.